model with two external channels.
Okay, thank you. So thanks to the organizers of this program and to Darren and Peter for inviting me to give a talk here. It's my pleasure to be here in Cambridge, as always. And also thank you for coming up for this third talk this morning. So I will talk about a problem having to do with points on the sphere and point distributions. And this is a joint work with Juan Criado del Rey, who is the postdoc in Leuven. And we have a paper posted on the archive just last month. And there's also ongoing work with Juan and with Ellen Groth, who is a PhD student. And so I will give an introduction to the main and state the main result that we have. And then I will take you through parts of the proof. And it's a blend of complex analysis, some potential theory, there's connections with equilibrium problems. So some of the things that we already seen in earlier talks in this workshop. At the end, there's also a connection with orthogonal polynomials, and I hope I will have time to also to explain you about that, because that's the new work, some new result that we have in with Juan and Ellen. That's not in this preprint, but that's a connection with orthogonal polynomials and maybe a first step to more detailed analysis of the problem. So the problem starts with the so-called spherical ensemble. So that's a way to distribute points on the unit sphere. So we have the unit sphere in 3 dimensions, and we want to put charged particles on this sphere in sort of an optimal way. So they should not be too close to each other and sort of uniformly distributed points. How to uniformly distribute points on the sphere. That's actually a famous problem. It's part of Smail's list of problems for the 21st century. Very specific way problem to how to do it in an optimal way. The spherical ensemble is a natural way to do it in a probabilistic setting. So you're going to take a probability measure on points on the sphere, and this is the probability density here. So your points x1 up to xn are on the unit sphere, and for each pair you take the distance, take the Euclidean distance here between 2 pairs. Probably the square is not there, should not be there in the way I've written it here. Yeah, sorry about that. And you take all mutual distances and take a product of all distances, right? That would be, and you take a prefactor here, partition function, to make this a probability density on n copies of S2. Right? So it means that if 2 points are very close, then of course the corresponding factor would be small, and there's a small likelihood of finding these particular particles that close to each other. Right? The way, so I said that 2 should not be there, sorry about that. By this particular form, it is nice because it has a determinantal structure behind it. So there are for correlations and so on between particles on the sphere. In this particular model, there are nice formulas with determinants. It's also an easy way, relatively easy way, to generate points on the sphere with in this way, which is a result of Krishnapur 10 years ago, and it goes like this. You take 2 random matrices, independent so-called GUE matrices. They appeared in Alfredo Deano's talk yesterday, I think. So these are square Hermitian matrices, and each entry is an independent Gaussian, and complex Gaussian, and up to hermiticity. Right? So take 2 copies of that, independent, and multiply A with B inverse. Right? So that would have that would no longer be Hermitian, but it will have eigenvalues all over in the complex plane. Sorry, it should probably be Ginebra matrices. Sorry about that. Yeah, should not be GUE matrices, I'm sorry. It should be two independent Ginebra matrices. And so they're not supposed to be emission, the A and the B. Sorry about that. But only complex Gaussian entries. Then you take this product, A times B inverse. Eigenvalues are all over in the plane. And you put them on the sphere by means of inverse stereographic projections. Then you get random points on the sphere, and they're exactly distributed according to this probability density. Yeah? That's now what we want to do is to put some external charges on the sphere that which are large charges, fixed charges compared to the other charges, and at certain locations. So here in this picture, there are three such external charges located at these three positions, and they also interact with the other charges in the same way, right? And altogether, there are still n free charges on the sphere, but there's an inner repulsion between the various charges, but there's also repulsion due to the external charges located at the points P1 up to PR, right? With certain strengths A1 up to AR, right? And this picture is taken from a paper of Brachard, Drakenev, and Sept and Womersley that appeared just last year. And so if these charges, each of these external charges will create a region around it that's free from the other charges. Right? And in the large n limit, which I'm interested in, because of the exponent n here, there will be some fixed domains that will be free from charges. Right? And then there is a part of the sphere where the free charges distribute themselves, right, with high probability. And we're interested in this free part. This is called the droplet, if you want. Yeah? And one result is that, also from the same paper with Brauchart and company, is that these charges are small, these AKs here that appear in the exponent. Then each particle here, pk, creates a region around it that's free from other particles. And these are spherical caps. Right? So this will be disjoint spherical caps. But if these charges are larger, then there's more repulsion, right, from each of these fixed charges. And then these spherical caps will grow bigger if the charges grow. And then after a while, they will start to overlap. So if you just take two charges in these pictures, again from the same paper of Brauchart and people, and start increasing these charges AK, then here are these two circles that are the boundaries of the spherical caps. But the actual droplet is smaller, right? Because now there's an overlap, so somehow the union of two spherical caps is too small. The complement here is a smaller droplet. And so the question that was left open in this paper, and what is the region that's occupied by these free charges? Right? So can we say something about it? In case of overlap. So in case of these AK, these charges are big. And our result deals with the situation when we have two external charges located at 2 points, P1 and P2, and the charges at each of these positions is the same. So we have two equal charges at these 2 points. And then we have a first somewhat surprising result. Then if we look at a situation where we put those, we can determine the droplet, and there's a nice description if you project it onto the plane by means of stereographical projection. And let's do it in such a way that these points are mapped to purely imaginary points. So IB, I noted here a minus IB, and B should be bigger than 1. It actually means that we put the North Pole, from which we do our stereographic projection, in between these two points. Right? So we rotate the sphere from this picture so that this midpoint here is the North Pole, and these 2 points are still in the upper half plane, sorry, the northern hemisphere, and then they project onto this, and we do our projection in this way. And the B is bigger than 1.
What is then D, the region D?
So the region D?
What is D? Uppercase D. C of D, right? What's D?
So I don't understand.
What is D?
D?
Uppercase D.
This one?
Yes.
Oh, D is the droplet here. That's the region which contains the particles in the large N limit. The red, yes, the red one, yes, exactly. Sorry about that. Yeah. So our result is with Juan that if this A is big enough, and this is the precise condition for that, and this D is indeed this region here, the red one, where the particles accumulate in the large N limit. If we project that onto the plane, you get a region omega, which will be compact region because the North Pole is outside in the blue part. But that turns out to be a region that's bounded by an ellipse, right? So, and the ellipse is in this particular form, right? So x squared, y squared with prescribed constants here. So that was kind of a surprise to us. However, I learned this morning from Björn Gustafsson that he has a paper in a work with Tekashiev from 2011, from which is very close to this one. So we still have to compare the two results. So it may have been not new, this one, but I still like to talk about this and take you to the proofs, because there are some more ingredients that are of interest, hopefully, to this audience. So let's see. So there's some potential theory coming in, right? So this is about a large n result, right? So we take a limit where n goes to infinity, right? Then this turns into a potential theory problem where we have an external field, right? This is very similar to what we saw in the last talk, and also yesterday, I guess. So, but here we are on the sphere. So if we have an external field, Q, which for us will be the potential of some measure, and the sigma you should think of as being this a sum of point masses, or just the 2 point masses, if you wish, right, for the particular result. So this is called the logarithmic potential. X and y are on the unit sphere now, but it's the same formula as before, as you all also would do on the real line or in the complex plane. And there is an equilibrium measure then that depends on this sigma that minimizes this double integral, this logarithmic energy, with respect to some probability measure mu, and this external field term, right? That involves this function q, which is in itself is some potential for our purposes. Okay, so there will be a unique probability measure that minimizes this, and that's the equilibrium measure in the external field generated by sigma. And that's exactly our setting. The sigma will be these 2 point masses, say, 2 Dirac masses at these 2 points, and the other masses, the free mass, will distribute itself as this measure mu sigma that minimizes this expression. That's what comes out of the potential theory. And our goal is to compute this equilibrium measure, mu sigma. Now, one thing is very nice here, if you are on the sphere, or more generally in the plane, if this sigma is such that if you look at the support of this equilibrium measure, that's the droplet, right, this d, if that is disjoint from the support of sigma, right, then what happens then is that this measure can be written down then explicitly. Given that you know the droplet, if you know the support, you can write down the measure explicitly. It's lambda sub d. Lambda is my notation for the Lebesgue measure, the normalized Lebesgue measure on the unit sphere. And lambda sub d means restriction of the normalized Lebesgue measure to the subset d, to the droplet d. So if you take that Lebesgue measure on d, normalize it to be a probability measure, then that will be the mu sigma, the equilibrium measure. Right? So it means that to determine, if you are in such a situation, it's enough to determine the droplet, then the measure on it is sort of automatic. It's just uniform measure restricted to this droplet. And there's also a formula then for the Lebesgue measure, the total mass, total area, say, of the droplet, that will be directly be computable in terms of the total mass of sigma. I emphasize that sigma need not be a probability measure. Right? The sigma where we start from can be more general and will be more general than that. Okay, so for us, this sigma is indeed, for this result that I stated, the sum of two Dirac point masses, each of strength A, and that will be definitely of such a situation. These sigmas are very much concentrated, and it means that they repel the other charges, and the mu sigma, the other charges will go away from these 2 points. Right? So that we're definitely in such a situation for this case. And for any discrete measure, it will be like that. Okay, so the goal is to find this droplet, and then we automatically know the measure on it. Now, our strategy is to go in a roundabout way to do this, that we look for another measure which is located inside the droplet, which we don't know yet, but we're going to first construct a measure sigma star, that we call sigma star. There's some dual problem, such that if we, which will also be a measure that's highly concentrated, it will be on a, it will not be on a point set, but it will be on a one-dimensional subset on the sphere. Actually, it will be on the big circle of on the sphere, separating these 2 points. And if we start from this sigma star and do the same equilibrium problem, right? So, meaning, yeah, you then start with this potential of sigma star and you minimize, etc. Because this measure is supposed to be highly concentrated, this measure mu sigma, the corresponding equilibrium measure, is also the Lebesgue measure on a subset, d star, and we look for it in such a way that the support of this other equilibrium measure is the complement. So that's here the thing in blue. So the d star, the support of this other measure, should be the complement, and then taking the closure because we want closed sets. Right? If we're able to find this sigma star, well, this is a notion that is in this context related to what's called the mother body of the domain D. So this sigma star will be located here inside this droplet D. So that will be our strategy, and then we will aim for variational conditions that are associated with these 2 equilibrium problems. Right? So these are the equilibrium variational conditions due to Frostman, well, already from the 1930s, that also apply in this problem on the sphere. So given this sigma, we look for this measure mu sigma, and the sum of the 2 potentials should be a constant on the droplet, and it should be at least equal to the same constant on the rest of the sphere. Actually, we will typically have, we will have a strict inequality. And this other problem, this dual problem, will have the same variational conditions, right? But everything has a star, right? Star is, okay, here for this complement, this dual problem. So this sum of this potential for the mother body and this other equilibrium measure, the sum again is a constant, some other constant on the complement now of the droplet, the star, and it should be greater than or equal, in fact it will be strictly greater on the complement. And these two problems are related to each other because we want that mu sigma and mu sigma star are Lebesgue measures restricted to two disjoint subsets of the sphere, right? Well, their interiors do not intersect, and it means that if you undo the normalization, right, for mu sigma and mu sigma star, so this mu sigma divided by this number 1 plus 2a will be just the Lebesgue measure restricted to d. Mu sigma star times this constant will be the Lebesgue measure restricted to the complement. So the sum of these two should be then equal to the Lebesgue measure, normalized Lebesgue measure on the whole sphere, right? Okay, so what are we going to do? We're going to construct sigma star. We're going to construct mu sigma basically by giving a formula for the droplet, which is this ellipse that I showed you. We're going to construct sigma star and then verify that all these inequalities are satisfied, right? And that's a proof, right? But we're going to do it with calculations that we will do in the complex plane. So we're going to move to the complex plane with this stereographic projection, and we construct some measure mu v, which will be on the real line. And if we then move it back to the sphere by means of inverse stereographic projection, this phi inverse is the inverse, right? And then this is then the pullback of this measure that we construct on the real line by means of this inverse stereographic projection times this constant. That will be this mother body measure, which will be on this big circle on the sphere, and mu v will be on the real line, right? And the mu v will be an equilibrium measure in an external field. But now we're on the real line. So we have an external field u sigma on the sphere, and now something on the real line comes up. So, okay. So we're going to look at this external field, but now on the real line. And so you may wonder, where does this come from? Okay, we played with it, of course, and for now I just pose this phi, right? And okay, we will see how it connects to the problem on the sphere. So what is this? So this is a function on the real line, x is on the real line. This b was the location of, after stereographic projection, IB was the location of these two external charges, one at IB, one at minus IB, the symmetric with respect to the real line. And so this sort of comes from that. But then there's also something happening at, where this logarithm becomes infinite, at IB inverse and IB minus IB inverse. There is some repulsion from there and attraction from here, so to speak. But together they make up some external field, and we're looking for a measure now on the real line, which minimizes this weighted energy problem. So again, the usual logarithmic energy plus an external field term involving now this v. Right? This v has a particular feature that at infinity, if you think about it, x goes to infinity. What does the v? What does it look like at infinity? So this is like log x squared. This is again log x squared. It grows just like log x as x goes to plus infinity, and log of modulus x to minus infinity. This is only a slow growth at infinity. This is called a weakly admissible external field. So typically one asks for a faster growth at infinity, and then the equilibrium measure will have a compact support. But in this weakly admissible case, it's just a boundary case actually. The measure, the minimizer, which I call mu sub v, it could have an unbounded support. And actually that's the transition that will take place if we play with the parameter. So if we fix b and increase a, then that from the point of view of looking out on the sphere, small a means separated caps, and then it will turn out that this mother body measure will be on the full the full big circle, which translates to this problem as that the minimizer here will have full support on the whole real line. And if A is larger, so that the two caps are overlapping, and we have a droplet which is not the complement of two spherical caps, then this minimizer mu v here will have a bounded support. That's actually the case we're interested in. Okay, so this we can actually solve completely. To this equilibrium problem we can solve explicitly. It looks a bit horrible maybe, but the thing is that if A is larger than this critical value, depending on B, then the support is a compact interval minus capital A, and this is the formula for capital A. And if you're quick, you can see that this condition exactly means that there's no, that this square root thing here is just positive, right? And otherwise you just believe me. And then, and on this interval there is a density then for this equilibrium measure here. This is just a constant, explicit constant, but and here is the square root factor that vanishes like a square root at both endpoints, and there's a rational denominator here, where you see the poles located at 4 points on the imaginary axis. Right? The poles here are at, for this one, it's at plus or minus IB. These are these projected points onto the imaginary axis. The other poles are at plus or minus IB inverse. They're also on the imaginary axis. And they actually have an interpretation here for the spherical model, because they are the projections of the antipodal points of the two points P1, P2, if you do your stereographical projection onto the plane. So anyway, this can be done explicitly, and there's a recent paper actually of Orive, Sanchez-Lara, and Wilonsky, where they also consider these external fields, and they show that for A smaller than its critical value, the equilibrium measure is indeed support on the full real line, and for A bigger, that it's a subset, a compact subset, an interval, but they did not calculate the density like this. So how does that work? Well, I cannot go through all the details, but let me give you something, because this will be important, how to connect it to the sphere. There is a method called Schiffer variation. So we're dealing with a minimization problem for measures on the real line, and you can make variations of the measure, and if you embed your minimizer into a one-parameter family of measures, then the energy, of course, should be minimum at the minimizer, and differentiating with the practical parameter, you get an equation. If you do it in a specific way named after Schiffer, you get equations that you can translate into identities, an identity for the Stieltjes transform here of Cauchy transform, I call it Stieltjes transform here, of your equilibrium measure. So this is for Z in the complex plane. This Stieltjes transform minus the derivative of your external field, which will be a rational expression, because V has logarithms, right? So the derivative will be rational. This difference squared will be a rational function. It's quite special, but okay. But you can do the calculation, and that comes out. And so you will see that the poles will be double poles, because of the V prime will have poles at these 4 points on the imaginary axis, because of the square, this will turn into double poles of R at these same locations. And then you can look at what the behavior at infinity of the left-hand side here, for z going to infinity in the complex plane, and also for z going to these special points, the poles here on the imaginary axis. You get some equations for the coefficients that you would need to make the numerator here of your rational function R. Okay, you have to analyze that, what is happening, but if the support is not a full real line, then what comes out of this analysis is that the numerator should be a quadratic expression, and because of symmetry, it's just z squared minus some number a squared times a constant. Right? And this a is exactly what I showed you before. Right? And having that, we basically know what is the Stieltjes transform. Right? We just take a square root with the appropriate sign of R and add v prime. Then we know our Stieltjes transform, and then we can use Stieltjes inversion formula, Stieltjes inversion formula, to recover the density of our equilibrium measure. It will be basically, the support will be where this is negative, so it means indeed between minus a and a here, where the top is negative. We take the square root of the negative part of R and divide by pi. That will give us a density, and that's a result. But you have to take from this also the fact that we have an explicit expression for the Cauchy transform here of our equilibrium measure. Okay, so how are we going to use this to connect this problem to the sphere, to the spherical problem? Well, recall that I gave you this formula for the ellipse, right, which also came out of the blue. So this there is the notion, if you have a nice smooth analytic curve, there's a notion of a Schwarz function. Sort of implement some reflection into this smooth curve. Here I would like to have what I call a spherical Schwarz function that takes into account the fact that we're dealing with a problem coming from the sphere, the spherical metric, so to speak. So what we can build is a function S, which out of this Cauchy transform here of this measure mu on the real line. Right, we recall it from the previous slide. We know this, we know explicitly. And then, okay, there's some other terms coming in here. Right? And the statement is that indeed if we have a big enough, then we can create this function S of a complex variable. It will be analytic away from the support of this measure mu v, with a pole also at plus or minus IB. And this will have the following connection with this ellipse, namely that if we evaluate S in Z, and Z is on the boundary of this ellipse, or on the ellipse itself, right, satisfies this equation, then Z bar over 1 plus mod Z squared is equal to this value of SZ. So the usual the usual Schwarz function would have such a property without this denominator here. Just Z bar is equal to the Schwarz function. That would characterize a curve with the Schwarz function. Here I have this modification because of a problem coming from the sphere. But if you think about it, these two notions are quite related, right? So because you can write mod Z squared as Z times Z bar, and then solve this equation for Z bar, and you get an expression of the usual Schwarz function in terms of this one. Actually, that's actually what we do. So it's just an explicit calculation, but okay, some ingenuity still, but okay, because we have an explicit expression for this Cauchy transform here, as I told you before. If you plug in this, we have to take minus the square root. If you plug that in, you get some horrible expression, and then you have to solve such an equation. It looks terrible, and it's sort of a bit of a miracle. I don't know why it happens, but you do the calculations and it works, right? Yeah. So I don't have any conceptual. This is actually the connection to the sphere, so that's my only reason why it should be this ellipse. That is the solution of this problem, and this is basically brute force calculation. Okay. Anyway, so what does it now mean for the ellipse? So now we have this ellipse again, and it will carry a natural measure that will come from this the droplet. You should project it. This has the Lebesgue measure on the sphere restricted to this droplet that you should then project onto the complex plane, onto omega, and the area that will lead to area measure. The capital A now denotes the area measure on the plane, but modified with this spherical metric, this 1 plus mod z squared squared. That's sort of, and a pi. That's sort of the projection of the Lebesgue measure if you project it on, push it forward to the complex plane. And now we restrict this to this ellipse omega, and a normalization 1 plus 2a. So that's a problem. So this is our first lemma, that actually this, what we write down here, is actually a probability measure, right? So it's not immediate, and that it satisfies a number of equalities and inequalities. So look at it. Let's look at it. So we constructed now two measures. One measure, mu v, is on the real line, on a finite interval actually. This finite interval actually is also related to this ellipse because it connects the two foci of the ellipse. Right? So mu v is supported inside of this ellipse, and it says here that the potential of this mu omega is the same as the potential of this measure that's located inside of it. At least it's the same on the complement of omega, in the exterior of the ellipse. So this is really the idea of mother body. You have some measure spread out over a two-dimensional domain, and it creates a certain potential in the exterior. The same potential can be created by a measure that's located on a smaller set, on a one-dimensional set in this case, and that's the mu v. And it also has the property that on the ellipse itself, on the interior of the ellipse, there's an inequality like this. Okay? Then there's a companion expression for the potential of this measure on omega, on the full ellipse. This basically gives you an expression for the potential in the exterior. In the interior, in omega itself, it's equal to, if we add this term with a logarithm induced by these 2 point masses now at minus IB and plus IB and minus IB with a strength A, and this term, then we get a constant on omega. And it's bigger than or equal to the same constant in the exterior of omega. And well, these properties actually translate into the if we have this, then if we translate it back to the sphere by inverse stereographic projection, you get actually the equalities and inequalities that you aim for, right? For your so your measure mu v will go to your sigma star up to a constant, and this mu omega will go to the Lebesgue measure on this droplet, again normalized. And if you do all the calculations, these relations, identities and inequalities, translate into the identities and inequalities that you need for its variational conditions. And this term here comes from the fact that we're dealing to compensate for the total masses here. So this is mu omega is total mass 1. Here there's like a potential from a measure located at this discrete measure at with mass A and minus A at plus and minus AB. This extra term comes from the change of variables, so to speak. Okay, so let's look at this proof of the equalities. So we're going to use some tools from our toolbox from complex analysis, right? So let's look at what we have inside in our. So this spherical Schwarz function allows us to calculate the Cauchy transform of this measure on omega with the spherical metric here. So this is, okay, pretty standard for people who know how things work with the Schwarz function, but let's go through it anyway. So let's try to calculate this Cauchy transform now with this measure on the full ellipse, right? Okay, this is just a definition of this mu omega. And then let's suppose that Z is in the exterior, right? If Z is in the interior, you have to do a little more work. You have to isolate first a disk around Z, and then do your green theorem. But let's suppose Z is in the exterior, right? So then we use the complex green theorem, namely that we can turn this integral over the 2D domain into an integral over the boundary, over the ellipse. A contour integral involving S prime over 1 plus mod S squared. So how does it work again, the complex green theorem? If you have such a contour integral over the boundary, it's differentiable in S and S bar. This is equal to the S bar derivative, right? And if you calculate the S bar derivative, you get an integral over the domain with area measure, and this should be an S. Sorry about the typo. The S bar derivative of this piece, it turns again into this one. So that's why we use the green theorem in the complex plane. Then we recall this property of this function S, namely that the boundary of omega is characterized by the fact that S bar over 1 plus mod S squared is equal to S. Right? So we get rid of the S bar, and also on this other piece, which is not analytic, and replace it by S, which is a nice analytic function. Well, with some branch cut, but still nice enough. And we have a contour integral of a function with more analyticity. Okay, perfect. And then we can just modify the contour here, and we move it to infinity, because there's some branch cut on minus AA inside the ellipse, but in the exterior there's only a pole, two poles at minus A, IB, and plus IB. So there is a contribution from the poles, that is this one, and also then from infinity there's a contribution, from S is Z, there is a contribution giving rise to this one, because Z is also in the exterior, and at infinity there's no contribution. And then we go back to our formula for S, and this combination is exactly the Cauchy transform of mu V. So it fits perfectly. And that we get identities of these Cauchy transforms in the exterior of our domain omega. And after integration, we get these expressions for the potential, for the equality of the potentials as well. You have to do more integration, and then you have that. Okay, and so the identity inside the ellipse is a little more complicated, but it basically follows this pattern. Then there are also inequalities we have to verify, and they use ideas from Laplacian growth and partial balayage. But in interest of time, I think I will skip this one if you want to know about it. And it uses ideas from Gustafsson in this direction. You can ask about it or during question time or on private. Okay, I sent you the slides will probably be available also here. Yeah, and then we can finish the proof. So I skipped this part because I want to say a few words at 10 minutes about the new work that we are now undertaking, which is in progress with Juan Criado del Rey and with Ellen Groth. And we look again at this distribution of particles on the sphere, and with these external sources, and we can project this also directly onto the complex plane, and with the stereographic projection. So if we call Zj the projected points from the xj's, and now I changed notation slightly, the ak's will now be the projections from the fixed particles, pk. Yeah, maybe I should have called them bk. It was a b before, right, or ib. Anyway, now the ak's are the points in the fixed points in the plane. Then you get a probability density for these projected points of this type. So this is again the van der Monde squared here. Now this formula is correct here. And from this part you get, for each projected pk, you get an extra factor here, interacting as well with the zj's, and of strength ck. I'll call it ck now instead of ak before. Sorry about that. And this is the part that comes from the change of variables going from the sphere to the plane. Right? This spherical measure translates into this one. And this is a determinantal point process on the plane. This one is on the sphere, and I told you there is a kernel here, and in this form it's built out of orthogonal polynomials. So I want to say the result we have about these orthogonal polynomials, and it's actually with 2D orthogonality, so orthogonality over the whole plane. So there's a general setup here. If you have such a distribution of points on the plane with a van der Monde product absolute value squared times some product of a function w acting on each particle, a non-negative function on the real valued on the plane, then you can consider the orthogonal polynomials with respect to this weight function and area measure, and consider the set of orthogonal polynomials. So pk is the degree k orthogonal polynomial. And then this correlation kernel is built out of the orthogonal polynomials up to degree n minus 1 in this way, like a Christoffel-Darboux formula, but with a complex conjugate here, and then a square root of a product of this weight function at two variables. And so to understand this determinantal point process better, you need to have your hand on the kernel, and then as a first step you want to get your hands on the orthogonal polynomials. This is the result I want to present, that we can say something more about the orthogonal polynomials. Well, in our case this weight comes out like this, right? This came from the change of variables to the plane, and this is this for each external charge we have such an extra factor here. Well, we can actually say something only, well, let's first compare it with some other model that has been studied before and was also mentioned by Alfredo de Llano yesterday. If we, instead of this background measure here like this coming from the sphere, you take a background measure that comes from a Ginebra ensemble, so points on the sphere that are on the unit disk, but they're constrained by an exponential minus mod z squared, right? With a number of, we could call it Fisher-Hartwig singularity. So at each, there's a number of ak where you put an extra factor here that interacts with the other points. There's a repulsion from these other points in the sphere, on the plane. Then there's a result of Barlow, Bertolali, and McLaughlin that says that if R is 1, if you have one such factor here, then you have orthogonal polynomials with a two-dimensional orthogonality, but they're also orthogonal on a contour. And they also satisfy an orthogonality relation like this. So there's a contour you see going around 0 and around A. So A is a positive number, and where the singularity is located here, and this Pn times a lower degree monomial times this analytic weight function now is 0, right? If you integrate over a contour. This is quite remarkable because what you have is now orthogonality on the contour, which is typically easier than two-dimensional orthogonality. And what you also have is that you lose the complex conjugation here. So in this orthogonality, there's a complex conjugate here. I want to point that out. But here, no longer. It's not a typo. This is what it should be. Right? And you may say, well, that's terrible. No complex conjugation, no L2 theory. But actually, from the point of view of asymptotic analysis and equilibrium problems and so on, this is much nicer, because now you can move your contour to where you want to go, up to certain limits, right? You cannot cross any poles. But this is a very useful result for asymptotic analysis. For R bigger than 2, so this is for R is 1, you have orthogonality also on a contour. For R is 2 or more, there's no longer orthogonality on a contour, but what's called multiple orthogonality on a contour. Okay, that's a recent result by Li and Yang. Okay. Now the question is, can we do something similar for R weight? So we don't have as a background weight the e to the minus mod z squared, but now we have this 1 plus mod z squared up with some certain exponent. We can do something in a very limited case so far. We're struggling hard to extend it. We can do it if we have two external charges on the plane, and one of them is at the North Pole that we project to infinity, right, if we do the stereographic projection, and the other charge is P1 is mapped to a number A, which we can take to be positive. And C1 and C2 are the charges at these two, P1 and P2. They need not be the same in this result. And then our result is that this planar orthogonality, right, with the complex conjugate here, and everything is real here, and the measure is real as well. This orthogonal polynomial here, it also satisfies an orthogonality condition on a contour. So that there's also an orthogonality on the contour with respect to on a curve that goes around 0, but not around another pole that we have here, which is not present immediately here, at minus A inverse. This is the pole. And there is this orthogonality measure, which is a rational expression. There's no complex conjugation here. I should also point out actually that the orthogonality measure depends on n. Depends on the degree of the polynomial that you're interested in. So for each, if you go one more, you change your orthogonality measure here as well. Okay, there's another actually good thing, not too bad. And so our proof of this result is basically mimicking the proof of Balogh and others for the other case. So I have slides, but unless you're very fast, I will not take you through it. And I will stop here and thank you for your attention.
So you said that for R bigger equal than 2, the result of Li and Yang connects with multiple orthogonal polynomials.
Yes.
Here you don't need multiple orthogonal polynomials, even if R is equal to 2.
Yeah, R is equal to 2, but I put one point at the infinity, right? So it projects onto the infinity. So it's in this formula, you'd only see the effect. There's one extra factor here, basically, right? The other point is hidden in the C2, which is an increase in the exponent downstairs, right? So in a way, you have this background measure and you have one more external field. But it's an open problem to, if R is 2 or more, and you have more factors of this type here upstairs, is there multiple orthogonality? I played with this and so far not successful. But Yeah, of course, good question. That's of course what we hope, that we have to find other configurations where we find the droplet explicitly, more or less, yeah. We have the feeling that the boundary, if you project onto the plane, will always be an algebraic curve. But there's no proof for that, but maybe Björn has some ideas. That's sort of reasonable to expect, but to identify it explicitly, yeah, Juan is now playing with the idea of putting 4 charges symmetrically on the plane, on a sphere. That would be a natural configuration, and you get some equilibrium problem if you follow this strategy combined on the real line and on the imaginary axis, but there's still a work in progress. Yeah. Thank you.